Okay, so last time implemented a very rudimentary version of add with carry ADC, and we just got absolute addressing mode working, and we didn't go any further than that, but I think it was tested quite thoroughly, so it's not such a bad thing. This time I'd just like to do a bit of cleanup on that and then implement the rest of the addressing modes. There is the caveat that we didn't do decimal mode. So didn't implement decimal mode. I'm going to leave that for now, but that is something we have to do. Decimal mode is binary coded decimal. So I'd have to look up exactly how that works in the 6502 and how it affects these registers when it does its addition and what happens in all these weird situations. But inherently, yeah, it's just storing decimal numbers encoded in the binary, I believe, but I've not looked too hard into it. So first thing I want to do is a very minor thing, but this test absolute, I called it tests and I never noticed that all the way through. So I'll just rename that. That's the first thing. ADC Absolute. Let's just give it a better name just because it was wrong. So there you go, I've used that everywhere. Let's just check that still compiles. Yep, and that's still passing the tests. The next thing to do probably is to just do a bit of tidy up on this implementation of add with carry. One of the things I'd like to tidy up is the fact that I'm doing this horrible thing to calculate the overflow. And I'm going to say I did cheat a bit. I did look in the I looked at the implementation of device emulator, and they actually theirs is much neater than mine, more concise, but they are actually doing it the same way. So it's quite reassuring to notice that they are doing it by finding out if the negative flag, the negative bit on the values was the same before, and then and if it's different afterwards or whatever. So if you get a negative plus a negative and you get a positive number, you know it's overflowed. So they were doing it the same way, they just did it a bit more concisely. Oh, and they'd implemented decimal mode. But other than that, it was about the same. So I think I can tidy this up, and we can see, because I deconstructed how they did it, and it's the most concise way of doing it. Whether it's more readable though, we'll see. So one of the first things, the easy one, is the 0 and negative flag being set. We already have a function to do that. Set 0 and negative flags, and all you have to do is pass in the value that you want. So I can do that and get rid of those, so that makes it a bit more concise, and we're reusing some code. So there you go, so that still passes, that's absolutely fine. And the next thing is this giant, so this is the overflow flag thing. So what we're actually doing here is we're looking at before the operation was done, we look at the two values that we're adding together, and we find out if they're negative flags on those two values is the same. So we're looking at, are we adding two negative numbers or are we adding two positive numbers? So that's what this bit does here. Yeah, and one of the things we're doing is we're doing the same operation twice here. We're doing it here, and that seems a little bit excessive. So I actually think one of the things to notice here is that we're saving a copy of the A value before we did the operation. And the only reason we need to do it is for this, I believe. Yeah. So actually, maybe we should take this part out, because this one here, we're just trying to find out if the negative flag has changed. We don't actually have to use the A register there. We can actually use the operand, and that's still fine, I think. So this just checks that, yeah, was the negative flags the same on the two values before, and has it changed afterwards? Meaning, has any of the values that we added together changed with the result? So I could use the operand instead of the old register, so that still works. And what that means is actually I don't really need to store the old value. All I really need to store is this. And I can do that up here by using the A register. Are sign bits the same? So that's what we're really looking for. We want to know if the sign bits of the value before are actually the same. So we could swap that out for that there. And now we don't need to store the old A register anymore. So that's a little less confusing. Let's just see if that still passes. Yeah, so it does. And the other thing I can do is I'm masking off the negative flag, then I'm doing the exclusive OR with the other value masked off with the negative flag. But I can actually make that a lot simpler by just doing the exclusive OR first and then ANDing it with the negative flag bit, I think. So that will give me, yeah, that will tell me if I exclusive OR these two things together, if the negative flags are the same, then I will get a 0 in the output of the negative flag bit. So I mask off the negative bit, and I'll either get a 0 if they're the same. I'll either get a 0 if they're both negative or a 0 if they're both positive. And that's all I'm looking for. I'm looking for a true value if they're both the same. So actually what I can do is just not that, I think. Does that work? Let's just see. So that's a slightly simpler way of doing that because I've got rid of, well, yeah, I've got rid of the equivalency operator. And I've just done it as a bunch of bit fiddling. So that should be the same, and it is. So the sign bits, this is just telling me, are the sign bits the same before we did the calculation? And then afterwards we can use it down here. So that's fine. And then this last bit, what have we got for this one? This has got the same problem that we can actually do. We actually want to know now at the end if they are different. And we can tell if they're different by exclusive ORing the A register, and well, this is the A register now after it happened with the negative flag bit. So that just gives me the value afterwards. And if that's a, now that will give me a 1 if they're different. So if they are different, let me get rid of that. If they are different after being the same, so it's gone from they were both the same and now they are different, that means it's overflowed, and that will give me wrong. Is that the opposite answer to what I want? I think that's the opposite answer. Oh, it's only failed on one test. That's not right though, is it? Yeah, I think, is the problem that it's this? Is it getting... Oh, it is, yeah. So that's the problem. It's like, because that negative flags, it's basically getting a value of 128 and it can't set that into this bit flag. So that's a bit of a problem. At least I know that works though. So now I suppose the other thing they can do, and this is what they did in the Vice simulator, is you can basically combine this if statement into this. So you can basically, rather than setting it to false and doing that, you can say, are the sign bits the same? And then, is this true? I think that's right. So let's just see if that's what we want. And I can get rid of all that now. And I've just made that way more compact. Hopefully this still works. Yeah. So you can see why having the test is really good here, because I can change the math, simplify it, and it still works. And now I don't think I need this now, because now it's the result of this AND statement. Is that right? It does seem to be passing there, but it's a bit concerning that you have to put that there, but then you don't when you do it like this. I don't know if that's just a weird way that the compiler works out. They both work, so I'm going to leave it as the more concise one. So that's just really trimmed down everything we had to do. We don't have to store the old operand anymore, but we do have to store this bool, and we're doing a lot less calculation, but we've basically still got an if statement in here because of this double ampersand here. We're saying if the sign bits are the same, and then if they are, we do this calculation. But certainly simplified that quite a lot, and it still seems to work. So I'm quite happy that that's better. It's definitely more readable. And the last thing is this one's got the same problem. We want to set the carry flag by knowing that we went over 255, and we're doing that by masking off the high bytes and then saying is it greater than 0. Now you'd like to be able to do that and just say is it greater than 255, and then you realize that doesn't work. So actually you should just do it like this. Yeah. So the sum is greater than 255. That means we've induced a carry. So there's just one less operation there. And I think that's as simple as this can get. I did notice in the Vice simulator they were doing the same thing I was doing, which was putting the byte into a bigger number. They actually put it into just a normal unsigned int and then did their calculation like that. So I'm happy that that is definitely a lot more concise. Is it more readable? I think so. It's more readable than the Vice version, which has got loads of macros and stuff in it, but still it's a very simple thing, so they're both quite readable. The next thing I'd like to do is just, I'd like to have an assert here really. I don't think we've put any asserts in here, but if the decimal flag has been set, then I'd just like to assert for now, and just to show that we didn't actually handle it. And let's add, I think I might just add a macro for an assert. I know there is an assert thing. But I'm just going to add my own. If condition is true, then I am going to, what am I going to do here? I'm going to throw a -1. Just so I can have something there to do something like that. I wonder if that is good enough to do an assert. So I'll leave that like that for now, just as more of a reminder than anything. This probably isn't great. The next thing I want to do is I don't want to have to rewrite this a million times for all these other addressing modes. And I think everything here will always be the same. Once you've got the address of the piece of memory, you don't actually care about this lot. I mean, you do care, but you only know that this stuff's always the same, because it does consume some cycles to read the byte, but it's always going to be the same. I think it's always going to be the same once you've got the address. Yeah, because this is just always works, and this just always consumes one cycle. So I think it's time to move this out into a function, and we'll put it in one of these lambdas like we did before. So here we go. So I'm going to make this reusable. You can see the only thing it needed was the address, and I'll copy that. So this, I'm just going to call this ADC, because it needs the cycles, it needs the memory, and it just needs an address. So it wants the operand address. That's right. So let's go back to where we were. So all this can go, and it just gets replaced with that. And I suppose in here I'll move that assert in there. And in theory, again, this doesn't change anything. Oh, what have I done? Unknown file error. Exception thrown in the test body. What? Is it this assert's failed? Oh, it did. Why is that assert failing? Why is that asserting? Oh, because I want if not condition. Whoops. That didn't assert before then, did it? Yeah. So I'm asserting that condition is true. So if I'm not got that condition, then I throw. What the hell was happening before when that didn't get thrown? Or was it something weird going there? Anyway, that proves my assert is working. So that simplifies that a lot, and you can see how that's going to make life a lot easier when we come to do the other addressing modes. So knowing what I know now about these other addressing modes, that this is going to be reused, I'm not going to do as extensive testing on the rest of the ADCs because we'll be here forever doing that. So I'm just going to test one addition on each one. Maybe I'll test this page crossing stuff on these. But other than that, this should be enough to start getting the rest of this stuff working. So let's just take one of the really basic tests. Which one? let's just add 2 unsigned numbers. So actually that's really, these tests are actually, don't say that they're doing absolute mode, do they? But now they're going to. Okay, let's just check that all still works. So I've just renamed the test a bit, and I'll take one of the just can add 2 unsigned numbers. I might just do one of these tests for each one of those. So ADC Immediate. And in fact, this already has screwed me because immediate mode doesn't read a byte. It just gets the byte passed in, doesn't it? So I may even have to refactor what I've already done to immediately get this one working. So this would be test ADC Immediate. So let's get that one working. So I'm only calling this once, but just in case I want to do another test, I'm going to do it again. I think we just do that for the immediate mode. It's 2 cycles. It's a quickie. And everything else in that test stays the same, does it? No, we've got to change this. So in this one, the operand just goes straight after it in memory. So that's a really simple one. I think we're just missing this. So this is immediate. Yeah, that's the one we're missing. We're just missing the definition here. 69. Okay. Right. So we've just got one basic test for that. Wouldn't be too hard to add more actually if we wanted to. If we just make this the same way we've done the other one. But let's go and implement that one first, because straight away I think I've made a mess of this, because I can't just do ADC from the address. I need to actually, I mean, it'd be nice because the rest of these are just going to take an address, but this one actually isn't. This one just takes in the actual byte, doesn't it? This one fetches a byte. So maybe I'll take the address part out and I'll actually pass in the operand instead to this. Which is annoying because, oh no, I can leave the assert in there. Yeah, I'll pass in the operand instead. I think that's the way to do this. So this guy has to read the address himself. So it's a little more wordy, but it's fine. It's get it with, oh, this is not, don't need this here. Is that right? Oh yeah, because we're passing in the operand. So I think that's refactored so that we don't pass in the address of the thing to read anymore. We just pass in the thing we're going to read, the thing we read. And that's really just to handle immediate mode. The other ones are all going to read from memory. I think that's, yeah. So that's fixed it. So we've had to refactor that just a little, but still most of the hard work, the heavy lifting, is just being done in there. Given the operand. Okay, that's not too bad. is it worth putting another test in? I mean, we can do one of these other tests. We could do the positive and negative number test. It's a shame I don't like even just keep these and just as like preset ones so that I can do this. ADC Immediate. So I don't know if it's overkill to do 2, but there you go, we've got 2 working. So that's immediate mode doing. Let's do the 0 page. So yeah, maybe I will just take these 2 tests and I'll do 0 page versions of them. Right, so 2 tests for that. Let's go implement that one. And this should be, these are all very similar because they're similar to this one. ADC Zero Page. Already have a function to do that. That's all we have to change, and the rest we're just calling the same functions we had before. Cool, so we got 0 page working. So let's do the same thing for 0 Page X. Okay, so that instruction is not handled. And this one should be same as this one, except with an X and an X. Yep. So we've done absolute, so that's the first 4 done already. Absolute X. So this is the one that has the extra page crossing nonsense. I don't know if it's worth testing that because we have actually already tested that in other places and we're going to call the same functions. I don't know that it's worth it. Let's test that. Let's copy absolute and do absolute X. Absolute X. This is the one that we do, yeah, that takes the extra cycle. And we've already tested that, so I'm not going to test that again. Okay. So absolute Y, is that exactly the same with the Y register? Yeah, it is. So let's do that one. Okay, so we've got to implement that one. Again, we've got the functions to do this. Y register, Y register. Another one done. What have we got left? Indirect X. Okay, took me a while, but I got there. That is Indirect X. And how confusing is that? It's, yeah, let me just go over it one more time. It's read the value of a 0 page address, add the X register to the 0 page address, and then from there, read a 16-bit address and then take the operand from there. so the effective address is 8,000, and that's just absolutely bats. Okay, now we can go and implement that one. I think that'll do it. Excellent. Right, we just got one more left, at least until we attack decimal mode. And indirect Y. Yes, is this going to pass? No, because I've not written it yet. Okay, let's write that one. Indirect Y, indirect Y. So that is ADC binary mode, not decimal mode, binary mode, pretty much handled. It'd be nice to know if we could write a little program that could add some numbers together, if that's a thing. We can actually add stuff now. That's amazing. It's been a long time coming, hasn't it? I think we've gone on long enough here. If we're going to write any more stuff to add, I'll do that in the next bit. But I'm going to say that is I'm going to say it's a success because I've got all these ADC tests running. So yeah, maybe next time I'll write a little program to test out ADC, and we can look at some of the other ones. We've still got subtract with carry actually as well to do, and all these other ones, compare, accumulate. These are probably easier, are they? And it's still got all the same addressing modes. So there's still quite a lot of instructions to go. They've all been hidden inside these, you know, possibly 8 instructions on that one and 8 instructions on that one, and a few of these as well. But we're getting there, nearly, probably plus 100, it's probably over 100 instructions working now. So I'm quite happy with that, and we'll just push on in the next video.